Good afternoon and a warm welcome to the last joint astronomical colloquium of the year 2018. It is with great pleasure that I welcome Henrik Beuther from the Max Planck Institute for Astronomy up the hill, the Königstuhl Mountain, who will be speaking to us about star formation over a very wide range of scales within our Milky Way galaxy. Let me start by saying a few words about the speaker. He's from Cologne, and he studied in Cologne, did his PhD in Bonn. After that, he moved across the Atlantic to work at the Harvard-Smithsonian Center for Astrophysics in Boston or in Cambridge. After that, he came back after this first year of postdoc to Heidelberg as eminöter fellow, so he founded a junior research group on star formation and ISM observations up at the Max Planck Institute, and he has been ever since. He is now staff, he's APL professor with us here at Heidelberg University, and he's very active in all kind of observations from the interstellar medium in our galaxy to high mass star formation, low mass star formation. He received an ERC consolidator grant 2 years ago, right? 3 years ago. Time is going quickly. And we will hear about some of the results from his ERC project in his talk today. So please let us welcome Henrik.
So yes, thanks a lot for inviting me to this colloquium today. It's really a pleasure to be here, and after 13 years here in Heidelberg, it's my first HDEC, so to speak. I think I just gave one for the Habilitation. That was a Blackboard talk here, so in this room. So therefore, that's kind of my first real talk in this room. So therefore, that's really nice. So I want to give you today kind of a tour de star formation over a vast range of scale. And what do I specifically really mean with the range of scales? What do I have in mind with this? So in principle, I want to start on extragalactic scales and want to look first at the bar spiral interface of an extragalactic system, NGC 3627, how the bar interface looks from that point of view, and from that on I will make my way slowly into our Milky Way, look first at the giant molecular filaments, so the largest scale structures, that's not the largest scale structures we probably have in molecular gas in our galaxy, and then we want to characterize those. The characterization is done to a large degree with our galactic plane survey Thor, and I will tell you more about what we are doing with this. From the characterization of the ISM, then we slowly make our way further inside, and then we want to talk about star formation, star forming regions, scales 1 parsec and smaller, down to 1,000 astronomical units. That's another large program. So Thor is done at the Very Large Array. Core is done at formerly known Plateau de Bure interferometer, and today it's NOEMA. And last but not least, I want to zoom even further inside and see what we can do with ALMA really on scales down to 20 astronomical units approximately. That's kind of so from kiloparsecs to hundreds and even below hundreds of AU. That's kind of the road I want to show you today. So let's start extragalactic. So let's start with NGC 3627. Why do I, as a galactic astronomer, do care about this? That one could ask for. And in the end, my motivation stems, as usual, from galactic science. And we studied over years a lot this region here, that's W43. It's a very strong star-forming region at the interface of the bar with the Scutum Centaurus spiral arm. We did several studies of this, also other groups worked on this. It's really one of the most active star-forming regions we have in our Milky Way. But it's, You see it's going almost towards the galactic center, many spiral arms, many confusing structure, and the data are extremely difficult to interpret and hard to interpret. So this is just one CO spectrum towards the W43 region, and the main velocity component is that here around 100 kilometers, but there is a second velocity component here, and it's strongly debated whether this has nothing to do, whether it's simply kind of the next spiral arm here in the back, or whether it's a related cloud and that there is cloud-cloud interaction at the interface of the bar with the inner spiral. And I prefer the second interpretation, but honestly, from the Milky Way itself, to some degree, we have no good way to really answer whether these two components are unrelated or whether they are related and do interact. So that kind of brought us to the idea, let's look at an extragalactic system which looks kind of similar, and we may learn something more about this. And that brought us, by looking at nearby galaxies during the Heracles and the Things survey, this brought us to NGC 3627. What you see here is from the Heracles CO221 survey, a first moment map. These original data were from Adam Leroy, so nicely the rotation curve. Here is the bar, and in the archive of the plateau, there were high-resolution data of the two bar ends, so kind of the counterparts to our W43 in the Milky Way. So what we did, we simply took the archival data, combined them with the single-dish data, to really have all the spatial scales, to have reliable spectra, and to see whether we can learn something more from the interface of the spiral with the bar in this region and see whether this can be applied to our Milky Way. So how do these data look like? So in the following, by the way, if you see these color maps, in most cases, not in all, in most cases, these will be first moment maps, so intensity weighted velocity. So it's kind of a velocity structure you see here. So these are now, so we zoom now into the northern end and the southern end of this bar spiral interface, and again in color you see the first moment map of CO, and in contours it's the integrated emission of both these ends. So on the one hand, yes, one sees a lot of complex structure, one sees velocity gradients across. So okay, that looks reasonable. By the way, our spatial resolution here, the beam size is on the order of 50 parsec. So that's kind of what we can resolve at these distances. How do individual spectra at those positions look like? So I just selected two of them. So this is one spectrum. We see multiple velocity components. So here I did Duke Gaussian fits with the green, but in principle these are probably more. It was just hard to fit. Here it's two components. The detailed fits are not as important, but the main point is, yes, we do have several velocity components, even in such kind of a face-on configuration of a galaxy, and the velocity separation is similar to what we see also in our Milky Way for W43. So kind of this motivated us, or rather Sharon made, because she did the simulation coming in a moment, to model this galaxy, this NGC 3627, in a rather simple fashion, mainly modeling different velocities for the bar and for the spiral, and then see whether these different models do look alike to the spectra. So how does that look in principle? So what is shown here, the y-axis is the angular frequency, and that's kind of omega is the angular frequency curve. The x-axis is the radius in arc seconds. The bar ends here, it looks like 50, but it's specifically at 49. Arc seconds. The rotational structure of the spiral is relatively well known, so that's also from older studies of the region. What the question here is, what's the rotation pattern of the bar? And in particular, where does the bar co-rotation radiusly? So the co-rotation kind of where the stars and the spiral co-rotate, as the word says, and is the co-rotation so we have two scenarios. The scenario one, so the spiral, that's kind of our given. This is given from observations. And so what we call here the bar one scenario, there the bar and the spiral rotate with different speeds, and the bar extends out to the co-rotation radius further out. And scenario two is that bar and spiral rotate at the same speeds, and the bar ends inside the co-rotation. So if we use this simple model and predict what the spectra at those positions should look like, that's what the colored bars here. So the red is the spiral velocity, so this is velocity and the fraction of profile. So the red and the green is the prediction for the scenario 2, and the blue is where the bar rotates at a different velocity. And clearly also, and the histogram shows all spectra, those of just the northern one in dashed and of the southern one in full lines. So what one clearly sees is that this higher velocity component is only reproducible if one has different velocities between the bar and the spiral. So, and these different rotation speeds between spar and spiral may be favorable to get really intense star formation. Yeah, so that this looks a lot like we see in W43, but obviously if it looks in the NGC 3627 similar to the Milky Way, this is no proof that W43 is the same scenario. It's just that these interaction between a bar with a spiral is a plausible scenario that may explain also our Milky Way structure. But yeah, it's not a firm proof, that is clear. So from these plausibility arguments between NGC 3627 and our Milky Way, let's now move into the Milky Way and let's look at where are the largest structures we have. The largest structures in the Milky Way, so one could call them giant molecular clouds. We were looking more for elongated structures, so in our following nomenclature, it's giant molecular filaments. So how can we find them and what is the structure? So let's have a look at that. There's an ongoing discussion since several years, triggered by several groups, that maybe the spiral arms are kind of built out of very long filament structures, and Alyssa Goodman from the CFA, for example, coined this term skeleton of the Milky Way, so that these giant molecular filaments may be something like a skeleton. In a project over several years, we tried to identify and characterize these kind of things. And how to do this? So in an early work, we started really visually, so we went into large-scale extinction maps of our Milky Way. So this is one example. 8 microns gray, blue contours is CO. So it's a bit hard to see, but there is really an extinction lane going through this structure. Just extinction could be also different distances. That would not be firm that we see this at the same distance, but therefore we took complementary CO data and looked for velocity coherence, and if one does a position velocity cut through this long structure, one sees here, so that's the position velocity cut, and one sees that we so really at one velocity over a degree on the sky, these structures are velocity coherent, so they are really coherent structures on scales of 50 to 200 parsecs. So with this technique, we identified in the northern and southern hemisphere with different surveys 20 of those very large structures between, I said, 50 and 200 parsecs. Masses of these structures are 10 to the 5 and even higher solar masses. Dense gas structures are small, so most of these structures have 10% really in the densest spine-like filament, whereas 90% is in the more extended molecular cloud. But where are those things located? So what we did then, we took the Milky Way model, so this is galactic longitude versus velocity, so this is really the observational plane, and these different spiral arms are Milky Way model arms from the model from Mark Reed, which he did together with Tom Dame. And yeah, galactic longitude, velocity is exactly how observable. And so we put our filaments into this model, and we see that most are associated with the Sagittarius Carina arm, but also others. We can then, since this is a model, we can also kind of deproject this and get a bird's eye view on our Milky Way. So here in this bird's eye view, now again we have here the spiral arm structures, and we do see that many of these filaments are located close to the spiral arms, but not all of them, yeah? So we clearly also have structures which seem to be in interarm regions, and if one thinks of extragalactic systems, again, there are, for example, these spurs, these star-forming regions, which are kind of loosening of the spiral arms. And it may be that these kind of structures in our Milky Way may resemble the spurs, but what this tells us is really that that environment clearly matters. So we have different regions, whether they are directly associated with the arms or in the interarm region, and that the environment does play its role in describing these structures. From these pure existence and location in the Milky Way, we then obviously, as a next step, we want to characterize these structures. And the characterization, for example, one can do different approaches, but is, for example, done here with the Thor survey. And what is Thor? So several of you know this, but for those of you who don't know the Thor survey, let's have a short overview what Thor is and also about the specs of Thor. So Thor is a very large program at the VLA. Thor is H1, OH, and recombination line survey of the Milky Way, of the inner Milky Way. These three words already say H1, atomic gas, OH, molecular gas, recom lines, ionized gas. So we are doing in one survey the different phases of the ISM, from ionized to molecular to atomic. It's around 120 square degrees on the sky, between 15 and 65 degrees, around 15 arc-second resolution. That's about a factor 4 improvement. And we started this project a few years ago, but it's still an ongoing project, and I will show new results. But in principle, the survey is described here in a paper in 2016, but more important, this webpage here, because there are all the other papers listed, and also 50%, no, more than 50% of the data are already public, more than 50%. More to come, but if you're interested in these kind of data, please visit the website, and if those data you need are not there yet, contact us. We can provide also additional data. So just to show you the improvement in spatial resolution, let's take this tiny region down here. This was the data set at 1.4 gigahertz before our survey. This is the new one, so one clearly sees much more detail, higher sensitivity, so the spatial resolution is a vast improvement. To get a little bit an overview, let's have a look at the full survey and the continuum emission first. So what you will see in a moment is a movie going through galactic longitude at the bottom, galactic latitude plus minus 1.2, and it's the continuum. So now this should hopefully start. Yes, it does. So in principle we have 10,000 sources, but in the outer galaxy it's less exciting, it's more point source background, but the further we get inside, you will see more extended structures. Here's the galactic H2 region. We will see several supernova remnants. This is here. That's a mixture of an H2 region with a supernova remnant. So important in the survey is that we do have all data from 1 to 2 gigahertz. So we have for each source a spectral index, and the spectral index tells us the physics. So negative is most likely synchrotron emission, positive can be optically thick H2 regions, or around 0 is optically thin H2 regions. So we can characterize the physics of all these data, and the whole survey, the continuum data with all the spectral indices are just published recently by Yuan Wang, who's also sitting here in the audience. So all these data are available, but it's not just the continuum, we have also the spectral line data, and in particular I would like to show you the H1 data. So here the bottom panel is the same continuum data set you just saw in the previous movie. That's the same, again from 67 down to 16, 17 degrees. And in the top panel, as soon as I start, will be the channel map going through the H1 data from starting at minus 113, and it will go through the channels to plus 120-ish, I think. So you will see in a moment, yes, so now we see the H1 structure at negative high velocities going to 0, and we do see in principle all the H1 structure of our inner Milky Way. And H1, since it's so diffuse, we do not just see the spiral arms, we also see all the interarm gas. So that's making life also so difficult that we see everything. So let's look at some of the H1 data in a little bit more detail, and in particular at the H1 self-absorption data. So this is one Of the giant molecular filaments I talked in the previous section, I would say, about. So this is at between 34 and 37 degree. The top panel shows you the integrated CO emission between 50 and 60 kilometers. So that's really one of these giant molecular filaments, a length of approximately 200 parsecs. And in the bottom panel are, for comparison, our H1 data. So the color is the integrated H1 emission, and the contours is the same CO stuff. Yes, the contours in top and bottom are the same. So what one already sees just visually here is that there where the CO emission is high, the intensity of the H1 is decreased. What means decreased H1 intensity? If one now takes a spectrum at any of these positions, so that's the spectrum. So that's why I think the H1 spectra are hard to see. So you see in H1 between 0 and 100, there's everywhere emission. If you would do this in carbon monoxide, you would have a few isolated components, because the carbon monoxide just traces the dense gas, whereas we see also all the interarm gas. But the important part is the velocity we have integrated here. That's the region where we have these dip in the spectrum. This is the so-called H1 self-absorption, or HISA. Yeah, so, and this HISA is very useful because one can fit kind of a baseline to the data, invert this, and with the inversion one can infer an optical depth. And the inversion is kind of a nice Gaussian spectrum where one can do all the gas kinematics from. And one should say an important feature is the emission here. H1 traces always a mixture of the warm neutral medium and the cold neutral medium. In the emission it's very hard to differentiate, but the H1 self-absorption profile, that's just the cold neutral medium. Yeah, so with these H1 self-absorption, or the so-called HISA, we have the chance to study the CNM, the cold neutral medium, in much more detail. So what was then done also here by, again, Yon Wang and Simon Beer in the past, they inverted these spectra and produced afterwards from these inversion pixel by pixel a HISA, one could say an emission map. Well, it's maybe a strange formulation, but a HISA map. And since these are nice Gaussian spectra, they are afterwards super easy to compare to our CO data. That makes the comparison easier. So how do the velocity structure of this HISA here compare to the CO? So in the top panel, first moment map, you see here the velocities between 50 and 60. This is CO, carbon monoxide, from the so-called GRS survey, the galactic ring survey. And the bottom panel shows you the same region on the sky with the HISA, so the Gaussian fits to these absorption spectra. Same velocity range, so even visually sees, okay, these two structures seem to trace similar gas kinematics. Yeah, so that's something what one can straight away. But we know that this region here, encircled by the blue polygon, is almost starless. This is almost no star formation taking place here, whereas in this region here, there is an H2 region at the center. We have feedback processes, more to come from this region. So there is really physical differentiation. So let's see how these two regions compare, left starless, right with emission, with star formation. So these are two histograms, velocity, number of features, and blue CO, black H1, and no big variation. So one could say the velocities in the starless part, where not much happens, is almost the same. So H1 and CO seem to be well mixed, seem to be well correlated. If we go to the other side here, where the feedback is, one clearly sees that the blue CO is 2 to 3 kilometers offset from the H1. So it seems that there is that the feedback really displaces kind of the velocities between the atomic and molecular gas. This is the first large-scale study we're doing for this cloud. We have 5 to 10 more in our sample we have to analyze in more depth, but we seem to see these feedback signatures in the velocity, and I will come back to this in a moment with a different approach. But these data allow us to do more. So probability density distribution of column densities, this was done since almost 10 years, very much from extinction data and what we can learn from this. With these CO and H1 data, we now have the chance to do the PDFs, probability of column densities, for the different phases. So I would like to show you how that looks. So the left panel, so it's always normalized column density and the probability density. The left panel is conducted from the emission data. So this is a mixture of warm neutral medium and cold neutral medium. The middle panel is done from the HESA, so this is just the CNM. And the right panel is the molecular gas. And the first thing you see is kind of that here, what I plot here is always the sigma, so that's the width of the log normal. And one sees that from the warm neutral medium, 0.14, cold, 0.3, molecular gas, the width of the PDF increases. This makes sense from a picture that in the turbulent H1, the column density is almost everywhere the same, so therefore the width is very narrow on the left side, whereas the further you go to the right, more happens. In particular, gravity takes over, the whole thing collapses, you get more structure in the column densities, and therefore the width of these things increases. So we have here really separated column density PDFs between the warm, the cold, and the molecular phase. And then, work in progress, we combined all these and got one together, and yeah, even that works. So we get even there an almost log normal distribution with maybe some tail here to be discussed, but our molecular data are not really sensitive enough for this. So I wouldn't overinterpret this, but the combined data seem also to go in the direction of log normal. But this is kind of fresh from the press. You created that more or less the last couple of weeks, so this is where we have to work more on this. But these data really allow us to set the different phases of the ISM into context and study their properties. A very different approach to do this has recently been developed here from Juan Soler. And I'd just like to show you a little bit what we do with this. So what is this approach? So this is the so-called histogram of oriented gradient. So the terminology hawk. You may hear the word hawk in the future a bit more. So what is this really? Just before I show you the real science data, what's the method? So what Juan here just put in the background is city and some landscape, and in both cases in the foreground Godzilla. And what is then done for both of these maps, you derive the gradient maps. So you have two vector fields. Then with these two vector fields, you can get the dot product. And with these dot product, you get an angle distribution. And if you do this with these two images, what you get is this angle distribution. And with these deriving gradients, so histogram of oriented gradients, so that this is the oriented gradients, you clearly find the common part of these two images. By the way, one interesting thing is I usually cannot excite my kids with our science. That was the first slide I ever excited my kids with yesterday. So I thought, okay, that's going, we get them with that. So I thought that was, I rarely get them otherwise. But yeah, so this is really kind of the idea. We want to find common structures automized within these maps. So that's the example. How does this look in real data? So on the left, in green, green teal, you see the integrated H1 at 55 kilometers, and in red, it's the corresponding CO map. By the way, this is this region here. If you wonder in the future, this is kind of our reference field where also the H2 region is included. So almost there. So this is the integrated emission. So one sees the CO seems to be embedded in the H1. So if we now put the gradient, so that's the gradient of the intensity of the H1. So we see strong gradients. That's the gradient map of the CO. And if we then again get the dot product from these two gradients, we get here this map on the right side where we see corresponding structures. One can now ask, what does that tell us? Does it tell us anything at all? How important are these things? So Juan then went in great depth to use different statistical tests, how to approach these things with the mean resultant vector, the projected Rayleigh statistics, different things. And I just want to show you one example here. So these are the projected Rayleigh statistics. So what is plotted here? So this is the velocity of the CO. and this is the velocity of the H1. And yeah, so the color scale is these projected velocity Rayleigh statistics, and the higher the values, the more yellow, the stronger the correlations are. And what you see here first is that good, there is a clear correlation between the CO and the atomic gas. So a priori, it's not clear whether the H1 and the CO have to be well mixed, but this, I would say, is clear signature that they are well mixed. We now, so this is the diagonal, but I don't have a plot of this, but Juan found other regions, particularly around the H2 regions, where one finds much stronger signals offset from the diagonal. And these off from the diagonal regions are those where feedback comes into play. So what we are now, or Juan is now working on, he takes different simulations with turbulence, without, with feedback, without, and to identify what are the most important signatures we can get from these plots, kind of where they are correlated. But I would say for me it's more important to see the off-diagonal terms, because on the one hand they should be signatures of feedback, on the other hand they could also be signatures of cloud formation, of converging gas flows. So we're working on two different paths. We're taking the simulations to understand kind of the background physics of all this, how we can extract the physics into our observational domain, and on the other side we have our Thor survey with a vast coverage on the sky that then can compare to the simulation to really understand the feedback and also the cloud formation. I'm even more on the cloud formation side in more detail. Stay tuned, more to come. We are still in the exploratory phase, but it's a very promising approach where we hope to see a lot more in the future. This is the atomic part, but in Thor we do also have other phases, so I'd just like to show you a little bit on the molecular phase. So we do observe OH, so the molecular OH. So in the top you see an absorption spectrum against an extragalactic background source. We see here this is the velocity, several velocity components. Absorption can be converted in tau, so we know the optical depth, it's relatively low. We have comparison 13CO spectra, and yes, so there are counterparts, but there's some of the stuff where there's no CO counterpart. So this may be CO dark molecular gas. But we have there also, the bottom is H1, so there is H1 in these regions. So in the whole survey we have 45 spectral positions where it's strong enough to do this exercise. And Michael Rugel, former student here in Heidelberg, did these analysis in detail, and he plotted the OH abundance versus the H2 column density over these regions. And what one finds is that really the abundance is nothing constant. Yes, there's large scatter, but nevertheless the abundance do increase towards low column. So this kind of implies that the OH is a very good tracer of the low column molecular gas. So what other people would call the CO dark molecular phase. So phase which is definitely molecular, but which is, like one sees here in the CO, not really traceable, not studyable. This is kind of going to the denser side, but we have within Thor also the end stages, so to speak, the supernova remnants, which one also sees in the continuum. So therefore we're also working on the other side on the feedback process. I just want to, most of the talk is about star formation, but I will come back to this in a moment. Just a short detour to supernova remnants. So what can we do with supernova remnants? So if you compare radio 1.4 gigahertz with 8 micron glimpse, H2 regions, that's a known H2 region, emits in radio and at 8 micron. Supernova remnants, for example, on the other side, do have no really 8 micron counterpart. They are just strong in the radio. So this is a known one, and based on these characteristics we went through our survey and searched for new ones, and this here on the right side is a new supernova remnant candidate. Yeah, so one should confirm that later on, but doing this exercise over the whole survey we found 76 new candidates. So the red ones are the known supernova remnants, the green ones are the new ones. They are on average smaller, almost the size on average factor, almost factor 2 smaller. This is simply because we have much higher angular resolution. So with this approach we double the population of supernova remnants, which is kind of important because that's the one of the methods to get the turbulence into the ISM from the supernova feedback. If I understood the simulators right, we are still observationally a factor 2 below the number what theory we would like to have, but since with higher resolution we found as double as much as before, I think there are chances that more of those are hidden maybe at smaller angular scales. Yeah, so that was my little detour to the late stages, to the feedback. Let's come back to star formation, and let's look at individual star forming regions. And one way we're doing this is with NOEMA, or formerly Plateau de Bure interferometer, with a large program core. What is core, or what are the characteristics? We have observed 20 pretty well-known northern high-mass star-forming regions at 0.3 arc-second resolution. For the closest region we get down to 500 AU, for the further ones is more 1,000, 2,000, so it's a large program, 300 hours. And the goals of these projects, I would say, are fragmentation, disk formation, chemistry, outflows. So that's the range of goals we are following in this survey. To give you an overview how these things look like, so this is really, in the northern hemisphere, the highest resolution you can get. In the south, ALMA now gives us higher resolution, but for the north, that's the best you can get. And also large samples are even difficult to do with ALMA, so we can do statistical approaches. Well, 20 regions, how much statistic, that's one can debate, but that's the direction we are looking for. So how do these data look like? To give you one example about the continuum, in the following I converted all of them to linear scales. Yeah, so this is astronomical units, so the box size is 50,000 astronomical units, and what you see here is the 1.3 millimeter dust continuum emission. So it's really the dense dust and gas cores where the star formation takes place. That's our resolution element here. So these sources are really well resolved. One example, how does that look in the full sample? There it is. So this is, and it's all the same box sizes, yeah? So it's an identical figure. And for me, the first thing one sees is that there is a diversity in fragmentation, yeah? So we see regions which are almost single, like S106 or NGC's 7538 IS1. And in other regions like this one here or that, we see multiple cores, up to 20 substructures, which fragment a lot. So there is not a unique way to fragment these kind of regions. They are evolutionary-wise, we try to select them homogeneously. They're all so-called high-mass protostellar objects. So all greater 10 to the 4 solar lumina. So all star formation, it's not starless. They have all protostars inside, but it's still ongoing accretion. And if one looks at the separation of all these substructures and also the masses, these data are roughly consistent with thermal genes fragmentation, roughly. But the diversity tells us that this is definitely not all. And we're currently investigating further which is more important, whether it's the initial density structure, which does the different fragmentation properties, or whether it's the magnetic fields. These things have to be investigated. But first order, thermal genes kind of works. Second order, we have to understand a little bit more the fine details of this. But we then want to go into more detail, and I just want to give you a case study done by Aida Ahmadi, who is also here. We want to focus here on this region W3H2O, and we want to see whether we see disks inside and whether these disks may even fragment. So just to give you a zoom into this is again a first moment map of this region. Contours is the dust continuum, color first moment in methyl cyanide, beautiful red-blue shifted gradient. To first order one could think, oh, could that be already a disk? No, it's not. And also for a disk you would need to have the source here in the center. That's not the case. We have two sources here, so it's a rotating envelope. But one can go into detail and look at the subsources a bit more in detail. And so if one takes just, we cut the data here, or AIDA cut the data here, and one sees clearly a red-blue shifted gradient around the right side and a red-blue shifted gradient around the left, sorry, here, and the arrows show the outflows. So the outflows are perpendicular to our rotational structures. Are they Keplerian with our data with a spatial resolution borderline? They're at least consistent with this, but it's not really that we see at those scales. Yeah, so you see here the scales, our resolution element is approximately 1,000 astronomical units. The real Keplerian structures are probably smaller. So, okay, nevertheless, we have a rotating envelope, probably 2 protostars inside, likely with 2 disks associated. What else can we do? So we have all the spectral line data. Particular methyl cyanide, a ladder with many lines. One can now fit all these lines pixel by pixel and get for each pixel a temperature. So this pixel here is 207 Kelvin. But with this way, we get we get a temperature map. So we have detailed temperatures, and with a dust continuum, we have the column density. So in principle, we do have temperature, column, and rotational velocity. So these are the parameters one would need for a tumor analysis. So therefore, as a next step, we thought, okay, can we apply the tumor analysis, the classical tumor analysis, to these kind of data? And this is the tumor map AIDA derived. So the contours, the color is the tumor map, and the contours is again our dust continuum, and the 2 protostars are at these 2 stellar locations here. And high values imply stable, low values around 1, 2, that it can become unstable. So, and one sees, yes, around the protostar, very high values, stable as it should be. It's very hot there, high temperatures, high velocities. But it's interesting that here in these outer regions, so we really get tumor values around 1. And the contours I either put here on top are the highest resolution data, only 1 configuration of the array. And there seems also to be in the continuum a secondary peak. So this indicates that with this method we can really kind of predict the fragmentation on the smaller scales and on the disk scales. Yeah? So therefore we do see on the large scale what I showed in the continuum before, that's thermal core fragmentation, genes fragmentation. That's the large scale. But then on smaller scales we do see a different mode of fragmentation, and this different mode of fragmentation is then the disk fragmentation. So that takes place on the smaller scales, and we can, with this approach, we can study both regimes and do understand also the small scale disk where, and in these high mass regions we have high multiplicities, the disk should fragment. We need something like that to understand also the fragmentation. As a next step, now there were many caveats in the analysis, so we went to simulations to test our approach, and we now expand this to the full sample, and AIDA will work, or is currently working on the simulation part as well as on the full sample, and more results in a statistical sense for the rest of this will come out soon. Core has more, so we can also work in the chemical evolution. So this is a bit shorter, but I just want to highlight what we have. So we have for each peak this kind of spectrum, 4 gigahertz wide with many molecules. So we have the methyl cyanide, so these are really the very dense gas, what we also use for our temperature determination. We have outflow tracers like the 13CO is somewhere hidden. Then we have C18O. We have also deuterated species. Since this is a map, we have not just the spectra, but we have of each a spatial distribution. And just to show you some examples, they vary. The contour in all these maps is the dust. Methyl cyanide peaks on the dust. Deuterated DCN is peaks offset. CH2CO has a very diverse structure. Methanol is also in the outskirts. This analysis of this region was done by Caroline Gieser during her master thesis. She is now expanding this. It's including all the modeling. We try to understand the chemical evolution of high mass star formation, and this is just to give you a glimpse in the direction we are going and to do the whole sample from a chemical point of view. This is what is possible, I would say, in the northern hemisphere, but yes, ALMA does exist. So we can go to even higher resolution in the north with the VLA at centimeter wavelengths, in the south with ALMA. In the spirit of time constraints, I will really concentrate on the ALMA results of the southern hemisphere and what one can do there. So this is For this early ALMA study, we selected a southern well-known hot core for those people in the TOG 351, for those not hot core, very chemically rich, many spectral lines, very active. Early on, before ALMA, we did already studies of the warm gas with the Australian telescope array, and these are old data from 2009 or the data in 2008. Again, first moment map, this time in a highly excited ammonia line. One sees rotation of the whole thing perpendicular to the outflow. But you see here the scale, this is the envelope, 7,000 astronomical units in radii if you take the scale bar down here. So this is really the large scale envelope. How does that look if one now zooms at higher resolution? And our first study was at 0.06 arc seconds, so 60 milliarc seconds, done with ALMA at 690 gigahertz. And I now overblend, so the next plot has the same region, dust continuum, dense gas, but this region. So you see here, it's all the envelope, but if you zoom in, you see with ALMA we filter out to the large scale. So there is emission in principle in between, but with this filter out. So we do see 4 regions, 2 central ones, 3, 4. So to some degree also from the scales, this reminded me very much to the trapezium in Orion, for example. Yeah? So that there are these multiple structures within this, and if one now zooms into this even further, just into the central region, there are 2 ones. Here the triangles, these are methanol masers, and I was first excited to see, they're associated with one, but the absolute positions are uncertain. So the methanol masers, the triangles could be anywhere here. They could also be on this source, so we do not over-interpret this part. But we do also see clearly elongated structures here, yeah? And what one can do, so at 690 gigahertz, the dust continuum becomes optically thick. So one can use the absorption against the dust continuum and derive accretion rates. Redshifted absorption gives you infall. Okay, no, I should correct myself. It's not an accretion rate, it's an infall rate. We have redshifted absorption, and we see the infall on the scales of our data on 200 astronomical units. And we can derive infall rates on the order 10 to the minus 3 solar masses per year. That's pretty high, but that's exactly what is needed to form high-mass stars in a few 100,000 years. But again, it's not an accretion rate, it's an infall rate, but observationally at these young evolutionary stages, I would say that's the closest we can ever get to an accretion rate. So I think it's a good proxy for accretion. We have much more spectral lines and could do more, but I will skip over this and rather show you really kind of the highest resolution one can, I would say, today get at millimeter data. And we took the same region and observed it now with 16 kilometer baselines with ALMA, went down to 20 milliarc seconds. So it's really, that is super high resolution. So again, take the left figure for a moment, and then I will overblend you the new higher resolution data. So this is 1 millimeter. This source 8, 3, and these 2 in the middle, these were the 4 we have seen on the previous slide already. I can go back. Yeah, so these, the numbers are a little bit changed. That's maybe my fault. 1, 2, so these 4 ones are these here. But in the 1 millimeter data, we see even more, and I can now zoom into all these boxes here. Yeah, so then these are now the zooms, and we do see a lot. So these are again the 2 central sources, but we do see also here in the outskirts these kind of bend structures. My interpretation, but this is not really clear, is that these could be, we're missing again more than 90% of the flux. These could be maybe streamers where gas should flow inside, but we need more data to follow this. It's at least clear that we see a lot of substructures, and these are probably just parts of the envelope which are not very peaked. Let's zoom into the center. So at this high resolution, the brightness of the sources is 1000 Kelvin. Yeah, so it's super bright and high optical depth. And with these high brightnesses, almost all data are seen in absorption. Yeah, so these are spectra towards the main peak position, and you see all these data are seen in absorption, with a few exceptions. Here's a water line, there's a line, and I focus on this one here, because in this unit we have higher spectral resolution. So, and in the following, I will show you back one. I will. Oh, oops! I apologize. I was too fast for that. Duck. So I will focus on the source MM1 in the following, yeah, because that's where we do see the emission and of this emission line. So to see such a line in emission, it has to have excitation temperatures above 1000 Kelvin. And if one goes to the catalog, honestly, we didn't identify the line, yeah. So therefore, I just mentioned the frequency. It's an unidentified line, but it's probably some vibrationally excited line where the frequencies are not properly given in the catalogs. So how does that look? So I was first, so the contour is the dust continuum. I was first really excited. Highest velocity at the center. If one looks at a channel map, it's almost this butterfly structure, you know, from low mass. I'm always searching for disks. I thought, yes, finally I find my disk. Unfortunately, it's not really true, because if one looks at other data, this is the outflow direction. And I could show you the data. So this is SIO and CO. This is really the outflow direction. And if one zooms in at 690, we know our rotation is going this way. So rotation is perpendicular to our expected, or to my, what I was hoping for disk signatures. It's not a disk. So what we now think, so it's also elongated here. If you have turbulent entrainment of a jet with the ambient gas, you would also expect the same signatures, that we see the highest velocity close to the center. So our interpretation of these data is really that we see the innermost interface of the jet with the associated surrounding layered, I would say, molecular outflow. So it's clear from these data that the higher resolution start really painting a very different picture. And for many observatories, it's said they do transformational science, but with ALMA, I for the first time believe it, because also on the disk and others, we really see totally new things, not always easier. So it's not that these things make our interpretation and our life easier, but it's very exciting, the directions one can go and what's possible to be done in the years coming. Yeah, and I think after that trip over many orders of magnitudes and scales, from kiloparsecs down to 20 astronomical units, I think that brings me to the end. And instead of a summary of the different parts, I like to end on more general statements. On the one hand, I think star formation is a highly hierarchical process, and we see the fragmentation on all spatial scales. And the second one for me is kinematics are important wherever you go. So we see kinematic gas flows on the scales of the molecular clouds down to the innermost accretion, and in principle that's what we want to understand. How does the material flow from the large scale molecular clouds down onto our protostars? That's for me kind of the underlying question I like to understand better and I like to work on. So that's from my side. Thank you very much for your attention.
So, many thanks, Henrik, for this tour de force against all the scales of star formation, from the galaxy down to protostellar, maybe protoplanetary accretion disks. The podium is open for questions. Yes, I come to you, but let me make more light.
Thank you very much for your wonderful talk. I have two topics of my question. One is fragmentation, and the other one is filamentation. You called that the diversity of fragmentation is very diverse, and the evolutionary process is not homogeneous. Do you guys understand the rules of governing this process?
Well, I think we have different. So my impression is that it's dominated by thermal physics. So it's most of the separations between the cores and also the core masses are, I say roughly consistent with thermal genes fragmentation. So that's in the end thermal physics. But then other things come on top of this to give the diversity. And for example, if you have very steep density profiles, you expect less fragmentation than if you have very flat density profiles. So the initial conditions do matter significantly. And I think for me the third very important part are magnetic fields. Yeah? With magnetic fields you can suppress these things. So from our data, what we have so far, we can understand the thermal part, I would say, the thermal Jeans fragmentation, and we have to analyze the density structures. That's also possible. We have just not done this yet. That's on our to-do list. I have to do this part. And for the magnetic field, we are doing follow-up observations to do this. So I think these main processes, it's an interplay of those.
And the next question is the filamentation. Do you understand this process? Is it self-gravity or is it magneto-hydrodynamics?
It's probably a mixture of both. And then the question which is dominating, I think that is topic of diverse discussion, and I don't dare to answer that.
Okay, next question by Stefan Jordan.
Looking at your second picture, you show that many of the star formation regions are not really where one assumes that there are spiral arms, but also in between. The same picture arises when you look at the Gaia data, actually, and look for O and B stars. They don't really seem to concentrate in the region of the spiral arms, but there are also many in between. So that would be very consistent with that picture.
Wouldn't, I give the question back, wouldn't one even expect that the picture is to some degree worse for the stellar part because there's evolution and they are older? And I would have hoped that our young ones are more closer connected to the spiral arms than the older stuff you see in Gaia. But maybe that's just an expectation from my side.
I mean, O and B stars are very young stars.
The O stars at least, yes. So that's
if you limit yourself to O stars only, they have an extremely short lifetime. So
okay, so that should be similar.
That's true. Be very close to the location of the formation. So
yeah, agreed. That's true. That should be very close.
Sasha Honi?
Because I actually also had a question about exactly that figure. So naively, I would expect that if you're looking for structures on the sky, that you would have a bias to find structures that are happening to be more oriented in the plane of the sky. And what you show here is that because you're associating distances with velocities, you have a bias to assign them as being pointing away from the sun, right? I mean, you have many of them that are just pointing away because all the velocity structure that you see.
Well, I would say they're always angled, isn't it? It's kind of angled.
But
okay, this is really pointing away from the sky. Yeah, you're right. The most are pointing away. That is true.
So I was trying to figure out what is the right answer, because this is clearly wrong, and the bias in the plane of the sky is clearly also wrong. So how do you?
Why would you say it's clearly wrong? Sorry, I don't understand that.
I mean, if I would look for dark or elongated structures on the sky in a survey like you did, you would preferentially find ones that actually happen to be more in the plane of the sky than a random orientation.
Well, I would expect that my expectation would be associated with this, my expectation was associated with structure of the spiral arm, and therefore kind of, since the spiral arm has some angle to us, I would have expected the orientation of this because we have the dense gas. That would have been my starting point.
So what you have there, is that the orientation of the clouds, or is that the arrow bars?
No, that's the orientation we really take.
You always expect.
No, that's yes. So there is, So the real data comparison without the deprojection is 1 second. I'm almost there. So the left side, So that's really the data. So the elongation is L versus V. That's just data without any distance. And then you're right on the. If I take the next one. It's not doing this. Okay, I have to get here back. Here now, each velocity is converted into a distance. So there is a large uncertainty in the distance part. But for me, the more illuminating part is kind of the left one, because there I didn't do anything to the data. So that's the right side has the uncertainty of the kinematic distance. That's correct.
If I may, I had one other question. Just one point that I didn't understand. You said that the OH is a good tracer of the CO dark gas.
That's what we find, kind of, yes.
But in your plots, you divide by H2, which was measured how? Because if it is, I mean, so
in most cases, so since we did the velocity stuff, yeah, so there are error bars. So it's in principle we also trace this. So this is done with the CO data, and in those regions where no CO is detected, we took the 3 sigma upper limit as a column. Yeah, so because it was done with the CO data, you're right. So in those regions where we don't have a CO, how to do this, we took the 3 sigma upper limits of the CO.
So in that diagram, there are no CO dark.
Well, there are, so it's 3 sigma detection. We use 3 sigma values for those which are CO dark.
So there are arrows.
Yes, yeah, so yes, there are errors. That's correct. That's right. So it's an upper limit.
When you showed this collection of the plateau de Bure data, the background was quite different in his plots. So has that a physical meaning? Is the density pressure difference, and does that relate somehow to the structure of cores? Or? So
that the background looked different, that's a presentation part, because we kind of, with the interferometer, we have side lobe noise in the background, so that with different scaling. So in the figures, I would say you should not see the different backgrounds. So that's a presentation. But asking the sample was selected as homogeneous as possible, but there are variations. So it is not homogeneous, and there are also different evolutionary stages. To derive these parameters like the pressure, we haven't gone into depth, but there is definitely, it's not as homogeneous as we hoped in the beginning. That's probably a fair statement. We hope for more homogeneity.
So can I also intersect a question? I mean, you mentioned already magnetic fields as one of the main, organizing agent for ISM dynamics and star formation. What are the prospects in your core sample or the zoom-ins to get, for instance, from plateau de Bure polarization maps?
So from plateau de Bure, 0, because plateau de Bure doesn't do this, but it
will come, right? I mean, there's
no, it's currently not in the highest priority. So from the plateau, well, they have 2 polarization, but they don't produce the cross products you get. So it's technically possible with NOEMA, but it's not on the short-term horizon to come. They prioritize other things. So
they told us next year it should be available.
No.
Okay.
I have heard others. I would not but to answer your question, SMA can do this, and all our sources are submitted as proposal to the submillimeter array, and I would hope, say, within the next year that we get at least a decent subsample and know the magnetic field. But with NOEMA, I would not wait for the polarization part. But SMA can do this, so we can solve this problem, I would say.
Okay. Good. If I see no further questions, let me make 2 announcements. The first one is, because Henrik is a local speaker, no Nachsitzung. We don't go out for dinner. You know where to find him, so there is ample opportunity to speak with him either up the hill or down here in the city. The second announcement is we will have Lars Hörnqvist speaking in the first week of teaching in the new year. He will be speaking about the illustrious TNG simulation, about what we can learn about galaxy formation and evolution, large-scale structure formation from these sort of supercomputing simulations. With that, let me wish you Merry Christmas, happy, relaxing holidays without too much stress, hopefully some snow, and I hope we see each other well and healthy and in good mood in the new year. So with that, thanks again, Henrik.
Thank you.